So in the previous lecture, we've started to look at infinite dimensional optimization problems over the space of functions, and we introduced something such as this. Or if you would like to retain f for the time being, so be it. Yeah. And now we would like to see what would be a natural way to come up with conditions for optimality of a candidate f that you have chosen in this function null. So let's, for example, try the same trick that we did earlier in finite dimensional cases. Okay, let's consider another continuously differentiable function g. We'll be considering mostly these kind of functions, yeah, on which the function null is acting to lead to a scalar at the end of the day. So let's consider something like this and designate this as psi of alpha. I suppose with a small amount of work, it stands to reason that the condition for optimality in terms of psi would boil down to what? What should this be equal to? 0. You all agree? The reason being, well, suppose it isn't, expand psi in terms of alpha in the neighborhood of alpha is equal to 0. When psi alpha is equal to 0, psi of 0 is nothing but j of f. So if f has to be the optimal candidate, then in any direction if you perturb this candidate from f to f plus alpha g, you should be doing worse. Okay, so if you expand it in a Taylor series in alpha, around alpha is equal to 0, once again what happens? This is the first term in your expansion, yeah, alpha into psi prime alpha, yes, and then what happens? Psi prime alpha, if it does not vanish at alpha is equal to 0, where is the contradiction? Just recall. You have to just phrase it. Whatever we had said in terms of g earlier in finite dimensions, you have to rephrase it in terms of psi. Isn't it? Where was the contradiction? The sign. You should be actually increasing. As you perturb f to f plus alpha g, this j should spit out larger values. But is it possible always to do that? Because alpha can be both positive and negative. Yes, you can approach alpha is equal to 0 from the left and from the right. So if from one direction you are getting one particular sign, then from the other direction you will be getting the opposite sign. And therefore the only way to resolve that conflict is to equate this to 0. Yeah. I hope you are clear on this, right, that this is the condition that you need for optimality. So how do we wrap our head around this object now? Now suppose, this is where we say that suppose for all g in C1 and okay, so you can say that all g is basically the perturbation that is applied to f, and f naturally by now you are familiar that f has to meet certain terminal constraints as well in the normal setup, right? If it's a function after all, right? So usually you say that the function is defined over the interval from a to b, so f assumes a certain value at one endpoint a and certain other value at the other endpoint b. They could be the same value, but anyway, nonetheless, what do you think g should assume at those values, like ga and gb? shouldn't GA and GB be equal to 0? You might perturb the curve in between, but at the end points, if GA or GB is anything other than 0, then f plus alpha g is no longer a function that satisfies the terminal constraints, and therefore there is no point in plugging it in here. Yeah. So whatever value f might assume at a and b, f plus alpha g must also assume the same values at a and b. At the other points, the curve can vary within the interval a to b, but at the points a and b, the perturbed curve and the actual curve must agree, and therefore GA and GB must be equal to 0. So G, apart from being this continuously differentiable function, implicitly it is understood that its terminal conditions are such that a and b, at a and b, G vanishes. So there is no perturbation because the terminal points are like sacrosanct, they are fixed. So think about hanging a rope or a cable between two endpoints. If you are looking at all possible neighboring curves to a claimed optimal curve, the neighboring curves must also at least satisfy the endpoints. You are trying to find out all possible curves that pass through these 2 points at these values of x is equal to a and x is equal to b. And if the perturbed curve does not even satisfy the terminal constraint, then it is not a legit perturbed curve. Yeah. So that is implicit, I am not mentioning it here, but it is an important point, it will come back to us hopefully by the end of this or the next module. So what does it mean? Suppose for this G that you have chosen with GA is equal to GB equal to 0, yeah, and for alpha we have J of f plus alpha g is equal to J of f plus, this is a notation that we shall be using, evaluated at f along the direction of g, yeah, alpha times this plus higher order terms in alpha such that again limit O alpha by alpha as alpha tends to 0 vanishes. So these terms grow at a rate faster than alpha. Okay. Suppose this holds, then we say that this object is known as the first variation of G. Okay. May or may not exist. If it does, then this is known as the first variation. Why are we interested in this first variation? What do you think? If you take hint from what we did earlier, there is some connection between this first variation and this. What do you think that connection is going to be? Can you guess? You can take a guess. Whether you are right or wrong, we will see later. But what do you think could be the connection between this and this? No, we are not talking about tangents, we are talking about some condition for optimality. A derivative of? What do you mean by the derivative? You are probably hinting towards the right direction, but I just want to be a little more precise here. But keep trying. See, in terms of when we parameterize this in terms of alpha, we know that this is the condition for optimality. This fellow must vanish. And now suddenly we are again going back to this and saying, suppose this fellow can be written like so. Suppose this fellow can be written like so. Then just take a guess, what could be the connection between this condition What we are trying to do is this is just another artificial thing that we have cooked up as an intermediate step. Ultimately, you will give me some j, yeah, and some candidate f or f star to be checked. And I will have to derive some condition in terms of j at the end of the day, right? So this psi thing is something I have cooked up. It's not going to help me. If you ask me a question in terms of j, I have to answer with a condition in terms of j rather than a condition in terms of psi. You'll say, what is psi? I might say, oh, I have defined psi like this, but you will expect an answer in terms of j. Otherwise, it's an incomplete answer. So what do you think this is going to be?
The earlier was like we applied sigma mode with alpha dot variation of.
Yeah.
So let's say you put that same logic, then variation should be 0.
The first variation should be 0 is what you're guessing. Okay, very good. Now, this is where we will bring this. If you are familiar with this, excellent. Even if you are not, there is something called as a directional derivative. There are actually multiple notions of directional derivatives. Here we shall see that this is actually a Gauss derivative, a directional derivative. Why is a directional derivative important? You see, when you talk about the simple derivative, as in for a single variable function, there is only one way in which the function, the independent variable can proceed. But in multi-dimensional spaces and higher dimensional spaces, you have different directions. So in order for it to be differentiable from different directions, you assign some arbitrary direction. Say in 2 dimensions, in 2 variables, you have x and y as your independent variables. So f of x comma y, and you say f of x plus alpha h1 and y plus alpha h2, which is essentially going to talk about the derivative along the direction of the vector h1 comma h2, right? And then that's the directional derivative along h1 h2. The point is that you will say that this derivative exists when no matter which direction you approach it from, it's going to be differentiable, you're going to have the same limit. Whether it's going to be linear or not is another ask. So there are stronger notions of derivatives where you also require them to be linear and stuff like that. If you have heard of the term, again, excellent. If you have not to worry. We will not delve much deeper into that. There are things called Frechet derivatives, okay. So there are things that are differentiable in the sense of Gauss, and there are things that are differentiable in the sense of Frechet differentiable. If things are Frechet differentiable, they are definitely going to be Gauss differentiable, because Gauss is a weaker sense of differentiability, and the two derivatives will also agree. But just because something is Gauss differentiable does not mean that it will also be Frechet differentiable, okay. So these are just some facts, do not worry about it, but suffices to say that when you are talking about Frechet differentiations, this alpha parameterization is not something you do. You just take small functions. Here what you are saying is f plus alpha g. Now the norm of g could be a unit norm, some normalized function, yeah, and you are reducing the norm of the perturbation by controlling alpha. So it's like the norm of this thing is being scaled down only through alpha, through one particular medium. But when you say it's Frechet differentiable, the norm of the f itself has to be very small. It could be along any direction. But all possible small small functions with small norms along different directions. So it will be like, say, f plus g, okay, where this norm of g has to be itself restricted to be very small, and instead of having order alpha terms here, you will then have order norm of g terms here. So you immediately can at least get a hunch that this is a much stronger notion of differentiability, yeah. So things that are Frechet differentiable are of course going to be Gauss differentiable, because you have got all bases covered in this. But things are Gauss differentiable, it means you are actually not considering all these possibilities. They may not be Frechet differentiable, okay. But okay, we will not get too far into this. The main idea that I am trying to present here is that you can essentially write this as limit alpha tending to 0 j of f plus alpha g minus j of f upon alpha. So this is like the get to derivative of this j, but the argument of j is of course functions like so. Okay, it's a special case of get to derivative applied to this, and this, it will turn out whenever it exists, will be equal to this object that we've just. So the first variation of this j at f along the direction g. Okay, just to convince you that how to go about finding this using this limit here, let's consider an example. Suppose g is given by phi of fx dx between 0 to 1. Okay, so this will be right. So this is 1, this is 2. So of course 2 minus 1 gives me what? I can expand this. Suppose phi is also continuously differentiable. Yes? So you're all agreed on the fact that this is a functional, right? Once you carry out this integration, it's going to lead to a scalar. So this ingests some functions and spits out some scalars. So it is a functional. Yeah. Now if you take 2 minus 1, because phi is continuously differentiable, you can expand this in the Taylor series up to the first term. What would it be? J of f plus alpha g minus j of f is equal to phi of f, but that will get taken out by this, right? So what will you be left with? Alpha times phi prime, right? The derivative of phi with respect to its argument, and then what else? What is the derivative being taken with respect to? Isn't it? You're expanding in the Taylor series around alpha, right? So what's multiplied with alpha that comes out? G of x, isn't it? So this is integration 0 to 1 phi prime phi prime fx g of x dx. So what do you think is the first variation then in this case? Sorry? Okay, I think I've already missed the, this one should have this, no? Phi of fx plus phi prime of, am I missing something? No, the alpha is already here, right? That's already here. Yeah. So if you try to take the first variation of this, you'll have to let the limit alpha passing to 0, and you'll be left with essentially just this integral here. So indeed the Gauss derivative does allow you to find out the first variation, and that first variation essentially is tantamount to this, isn't it? Because of that definition there. And therefore, the first variation is equal to 0 essentially translates to the necessary condition for optimality. Right? Are we agreed on this? That this condition is very easy to see. Okay? And this condition, now if you translate it or fold it back to a condition in terms of J, essentially leads to the first variation, that is this object being equated to 0. Yeah. So we shall now take a closer look at some relevant types of J. You can cook up J to look like all different sorts of functionals, but the ones that we shall be interested in, particularly during this course, will have a particular form, a specific form. So, let us consider y is equal to fx is the kind of curves we have in mind. So, hereafter instead of writing f, we will write y. You can just say y as a function of x, okay. Just make this transition in your mind. The function fx is just y is equal to fx, okay. We will make this transition in our minds and we shall consider the j now as a function of y, because y replaces f hereafter, and it is given like this: a to b, this is the curly L known as the Lagrangian, not the alpha, okay, this is the L. Maybe I can just write this in this manner as a function of x, y and y prime dx, okay, subject to some given y at a is equal to y naught, y at b is equal to say y 1. That is the constraints, terminal constraints being given. What motivates consideration of such kinds of functionals? Well, you look back on the examples we had considered in the previous session, the previous lecture, right? The Brachistochrone problem. Does it fit with this? You will see it does. You look at Dido's problem, fits in with this. You look at the catenary equation, also fits in with this kind of a cost functional. What I am trying to motivate here is, of course, you can cook up other kinds of cost functionals and carry out your analysis, but a whole array of different cost functionals can be made to fit in within this setup. And that is specifically the reason why we shall be considering these kind of cost functionals in our course. Okay. There is a very crucial detail here. What do you think you are going to choose? Like, we are control systems engineers, or we like to think of ourselves as people who want to exert some influence, but there is no control here. Of course, you will say, oh, it is a catenary, it is nature's way of doing things, that is the way the catenary will hang. Yeah, Brachistochrone, it is just the gravitational field, we cannot manipulate that gravitational field, right. So, it is nature. But if nature were like the decider, what is it that nature is actually deciding? Because if we understand that, then we will also realize that when we have engineered systems or human made systems, through which term will we be able to exert our influence in order to optimize certain cost functions? So, in this is the thing that we will essentially be choosing. It is not very obvious or clear at this point, and that is essentially one of the drawbacks of I would say the calculus of variations approach as it stands. It does not immediately allow us to clearly see what role our choice plays. But I will just try to give you an idea If you make another small mental transition in your minds, we'll of course deal with much of that towards the latter half of this course. Think of x as time. So change x to t. Think of y as a function of t then instead of as a function of x. So it's not a curve in space, but rather a trajectory in time of some object that's moving, maybe a car, maybe a particle, maybe anything that you wish to give a trajectory to. Then this y dot, because the prime will then be replaced by a dot, d dt instead of d dx. If you have a particle which is like a single integrator, then the equation of that particle is given by y dot is equal to u, where u is your control. So in that case, this will appear like t, y of t and u. And in that language, it is very clear and it is very obvious that what you are essentially choosing is u. In turn, that u is influencing y and causing this thing to be optimal if you have chosen a suitable u. So what I am trying to do here is to draw your attention to the fact that although this appears nothing like the control systems problems that we think on a day-to-day basis, and you might be thinking, what is this doing in a course called optimal control? If you just make a small mental transition, we are still dealing with optimal control here. Let us not lose sight of that fact. Okay, we'll talk more about this later, of course, because the course is after all titled optimal control. So there's no way we are getting past this. But for now, I want you to appreciate that these are three independent variables. Of course, subject to the dynamics of the system, subject to how they are designed, this y prime affects y. But in so far as the cost goes, there is some cost to be incurred that might be explicit in terms of the x, some cost component that relates to y, and some cost component that relates to y prime. Yeah, so this is in general the most broad class of cost functionals we shall be considering in this course. You can take higher derivatives of y if you wish, but again, you know, in a vectored notation, if you know what I mean, in a state space notation, higher order systems can also be represented as x dot is equal to ax, or even nonlinear systems x dot is equal to fx. Okay, the dot being replaced by prime here because the independent variable is x. So you can always do that, but I'll say that okay, this for our practical purposes will suffice. Okay, so with that agreed upon, let us now dive deeper into what that condition of the first variation vanishing will translate to for a cost functional such as this. That's what we shall see next.